Hi there. In this video I'm going to show you a few things which will help you to get ready for the lecture on implicit differentiation. Have a look at these two curves in the plane. The one on the left is the graph of a function. This means that for each x value that is involved, there is precisely one corresponding y value. The curve on the right is not the graph of a function, as you can see by looking at the vertical line shown here, for instance, which intersects the curve at three different points. Both curves have tangent lines. The slope of a tangent line to the curve on the left can be calculated by explicit differentiation. For the curve on the right, we need another technique, and this will be the topic of the next lecture. It's called the technique of implicit differentiation. Let's have a look again at the first curve, which is the graph of a function. In this example, we have an explicit formula for the function, namely y is 3 times x to the power 3 times the natural logarithm of x. Given such an explicit formula f of x for the function, we can compute the derivative f prime by differentiating the function f. Alternatively, the derivative is often denoted by dy dx. The slope of the tangent line to the graph of this function at one of its points can be computed in the following way. You start with the explicit formula y is equal to f of x, then you compute the derivative of the function f for general x, and finally you evaluate the derivative for the specific values of x. The result is the slope of the tangent at the specific point. Now let's change our perspective by considering curves that are not the graph of a function. Have a look at this example. The circle with radius 3 and center in the origin. This is a well-defined curve in the plane, but it's not the graph of a function, as you can see by looking at the vertical line shown here, which intersects the circle at two separate points. Suppose you need to compute the slope of the tangent line to the circle at one of its points. How do you do this? We don't have an explicit formula in this case, because the equation of the circle is not an equation of the form y is equal to f of x. We can divide the circle in two parts, which can be described by explicit formulas, namely the upper half and the lower half. The two functions plus and minus the square root of 9 minus x squared are defined implicitly by the equation x squared plus y squared is equal to 9. Now suppose we want to find the slope of the tangent line at a point on the upper half of the circle. In that case, we take the explicit formula y is the square root of 9 minus x squared, and then we can compute a derivative in the usual way. And of course we can do the same for the points on the lower half of the circle. It appears that we can compute the slopes of the tangents to the circle in the usual way. So what exactly is the point we are trying to make here? Pay attention now. Since the square root of 9 minus x squared is equal to y for the points on the upper half of the circle, the derivative for points on the upper half can be written as minus x divided by y. This formula holds as well for the points on the lower half of the circle, because in those points the square root of 9 minus x squared is equal to minus y. So we have a single formula for the derivative which is valid for all points on the circle. You're going to learn a new technique in class that will enable you to find the formula dy dx is minus x divided by y for the derivative without actually determining explicit formulas for the functions first. This technique is called the technique of implicit differentiation. In the case of the circle, we still could calculate the slopes of the tangents without this new technique, but of course not all curves are as simple as a circle. Have a look at our second example. This equation describes a famous curve called the volume of Descartes. As in the previous example, this curve is not the graph of a function, it implicitly defines several functions. Again, we could focus on a part of the curve, For example, this red part here, which could be described by an explicit formula of the form y is equal to f of x. However, the computations to find an explicit formula for a part of this curve are far more difficult than in the case of a circle. So what do we do if we need to compute the slope of a tangent line? We use the technique of implicit differentiation. With this new technique, the slope of a tangent line to this curve can be computed without knowing an explicit formula y is equal to f of x. This is the power of the technique of implicit differentiation. You can find the formula for dy dx without having to find an explicit formula for y in terms of x first. You're going to learn in class how this technique works, and then of course not just for this curve, but for any curve which is given by some relation between the two variables x and y. See you then.